Shall we? Good afternoon. I need a little more oomph behind the microphone, please. Thank you. So we have talked the last time about bonding, and with this we are done with bonding so far. And I will review some of this in Friday's session, where I do a review session this coming Friday. I understand that there is a midterm on Monday, and everything I discuss today and I discuss on Friday will be part of the midterm. So gases that I discuss today will be part of the midterm. There's a review session tomorrow, the review session that is held every Thursday from 5 to 7 here. I think there will be some things reviewed, which may be part of the midterm. Also, what we discussed today will be part of the midterm, and what was in the homework will be part of the midterm. So we'll be starting a new section, and the section deals with gases. And we have heard about gases already in our first lecture, and maybe even in the second lecture. And we have seen that Avogadro's law says that at a fixed temperature, the number and fixed pressure, the number of particles is proportional to the volume. Okay, so the volume is proportional to the number of particles. We look at these gases as one molecule or atom or one little entity, and it is independent from the rest of them, okay? Because gases are rather dilute, and so these molecules don't come that close to each other, so there's no intermolecular forces, and we call this an ideal gas, or perfect gas, okay? The ideal gas, and we will learn about the ideal gas law. But let's go back a little bit in history. People did not always know what we know now, that they know about the air, and the air causes pressure on us, and that we need air to breathe. And so there was, when science sort of became started in terms of the modern age, in the 1600s, people were actually concerned about these gases. They sort of had an idea that these are gases, and they must exert some kind of a pressure on ourselves and on matter that we deal with. And so there was this gentleman, Torricelli, and he was a student of Galilei, and Torricelli, Battista Torricelli, he lived in the beginning of the 17th century, that's a while ago, and he lived from 1608 to 1647, and he designed the first barometer, the first pressure measurement equipment, pressure measuring equipment, and he also designed the first vacuum pump. Of course, they didn't have an electromotor there to pump the vacuum, so how to pump the air out of a closed space and then have no air in there. That's what vacuum is. There's just no air in there, okay? And so what he did is, he said, if this has pressure, this what we call air, then I would be able to measure that pressure. And he took a glass tube, and melted the one side off of the glass tube, was about that long and this thick, so like a finger thick. And then he filled it with mercury. And mercury is very not very viscous. And he filled it with mercury, and then it was filled, and he had a jar of mercury, and he put his thumb over it, turned it around, and put it in the jar. And so what happened is, there was a column of mercury stayed inside that glass tube. And so what this actually did, that looks like this here, this is the tube here, and he evacuated the tube before he filled in the mercury. I mean, this was not quite like this, but he evacuated and then filled in the mercury. And so you see that the pressure of the air pushes on that mercury here and pushes up that column of mercury. And we know now that the 760 millimeters of mercury is 1 atmosphere. That's the pressure that the air here at sea level exerts on mercury. If we would use water, that would be not very convenient. That column would be 10.3 meters high, okay, for the same pressure. If you make a manometer for water, kind of difficult to transport, you know. And this, of course, the pressure changes. If the pressure is less, then this mercury will be less high inside that column. So if you go, for example, somewhere in Colorado, which is pretty high, it's something like 550 millimeters. If you go to Tibet, I was in Tibet about 6 or 7 years ago, this is 12,500 feet high. It's about half of this only. 350 millimeters, that's the pressure. So you have a little hard time breathing to get enough air in your lungs, and oxygen especially. So this is the first manometer, or the first barometer by Battista Torricelli. And so the pressure is nothing but a force on a certain area, okay? And so we have a standard atmosphere. We say this 1 atm is an atmosphere. It's nothing but 760 millimeters of mercury. And of course the pressure changes. If you have a low pressure system like now, then we're getting rain in. If it's a high pressure system, usually it's nice and sunny weather. And so it's around 760 millimeters, and small changes we can indicate, and we can predict how the weather is going to be. And many of you have seen these round barometers where you have to tap on there, and the needle goes either back or forward, and it shows you high pressure or low pressure. So, and this is called after Torricelli. 760 millimeters of mercury is also 760 torr, and in the standard international system, SI system, it's 101,325 Pascal. These are all units of pressure, okay? So we have talked about pressure. Now let's go a little bit further in the century, and we're going to meet Robert Boyle. And Robert Boyle was an interesting Irish physicist. And again, he lived a little bit later. He was born in 1627 and died in 1691. And so that's still in the 17th century. He was interested, and we know this all, that you need air to breathe, and the air has to have oxygen. But they didn't know that. They sort of suspected this. And he had already this invention of, you can pull the air out of a container that was invented by Torricelli, a vacuum pump. So he had to hand crank this thing, of course. And so he said, okay, why don't we let's put a fly in there, and let's crank this up. Fly, dead, okay? Seems to need air, obviously. And then he said, why don't we use a mouse? Put the mouse in there, cranks it up, dead, okay? And he did this. He used the rabbit and the snake and the dog and all these things. And this is, of course, very sad nowadays. At the time, that was part of science, you know. That's how they recognized. And of course, I don't know if they did the human experiment. They never reported that, but I think they were smart enough to recognize that if these guys need air, then I think it must be the same thing with us. And so he did the suffocation experiment, but he did something much more important than that. It depends if it was more important. But he found the following relationship, the relationship between pressure of volume and volume of a gas at a constant temperature. So let me explain this to you. You have a syringe. Imagine a syringe, and the syringe, you have some, and you all did this probably. You put air in there, and you put on the other side of the syringe, don't have the needle in there. You hold it close, and you try to press it. It will be very hard, okay? So if you have the syringe, and so it would be closed here, and you have a large volume here, you want to decrease the volume, so you have to increase the pressure here, okay? So in order to make this smaller, this has a certain volume, we mark this here, and a certain pressure. Now I'm going to push the plunger, we will have a lot of these pictures of plungers, okay? Push that plunger into that piston, into that cylinder here. So I get this here. Now I have a smaller volume, okay? This I plot here, the smaller volume, this way here, but I have a higher pressure, okay? And now it's easy if you have a large volume to get the first volume reduction. But once the volume gets smaller and smaller, it will be harder and harder to decrease the volume. You need more and more pressure. And this will look like something like this. Now you have a very small volume, but you have a very high pressure. Okay? So because that high pressure in that volume. So this would be the volume small, but the pressure very high. So there's a relationship between the pressure and the volume. And the pressure of the volume of a gas, and we call it an ideal gas, or the perfect gas, is constant at constant temperature. All right? So you get a curve like this that's at a certain temperature. Now, if you have another temperature, pressure and volume is also still constant, but the curve will be not this one, but it will be a curve. Oh, no, it's not here yet. Okay? Let's do that. It will be a curve like this here, and I will show you this in a minute here. Okay? Or it will be a curve like this here, which is underneath here. Okay? Essentially parallel. So you can also plot this differently. You say this is a constant. That's for the specific gas. So you can say P is the constant divided by V. Right? And this is nothing but the equation for a straight line. Y is mx plus b, okay? And b is 0, because I don't have any, but m is the constant. And I plot this 1 over v. This is 1 over v, okay? That's the x is 1 over v. Again, p here against 1 over v, what would I get? A straight line. Wouldn't I get a straight line? Yes, I get a straight line at that temperature. And at another temperature, I would get another straight line. Here it is. I would get another straight line with a different slope, because the constant is different for the temperature. Okay? So we know now Boyle's law is pressure times volume at a constant temperature is a constant. Okay? Or the volume is a constant divided by the pressure. Or the pressure is a constant divided by the volume. Okay? All this if you have the same temperature. If you have a different temperature, you have a different constant. So, okay, this is Boyle's law. P times V is constant. So that means, yeah, if I have a substance and I decrease the pressure, what will happen to the volume? Will increase. Let's do an experiment. Let's do an experiment. I have these tasty concoctions here. These are called marshmallows. You see those? They are actually very delicious, you know. I like them. They're delicious. They have 25 calories, so I'm four pieces, serving size. So you need to take 4 and put them in like this. 100 calories, so that's 25. Would you like some? Okay, take them all. Okay, I eat that one. That's not so. It's a little damaged. How about you in the back there? Did you catch it? You caught it? You caught it. Very good. Okay. All right. Get these calories. So they are very fluffy, and they are fluffy because there's air in there, isn't there? The air. They have some membranes and air. So now let's put this in a vacuum. It's not going to be a dog. It's a marshmallow. Okay. And so let's see what happens if we pull the air out of this thing. And we have here a desiccant, and there's a vacuum pump. Of course, in the old days, they had to hand crank this. When Boyle did his experiments, it wasn't quite as sophisticated. This is pretty old, actually, but not from Boyle's time. So Karen will show us what happens to these marshmallows. So we take the air out in a little wide angle, a little wider. Go a little bit away. Yes, a little bit more. Yes, excellent. And so, Karen, are we ready? So you see what's happening? Ooh. P times V is a constant. I decrease the pressure, the volume goes up. Okay? And so what happens when they totally expanded, the membranes break and they collapse a little bit. But now, if you put air on there again, there they are. They don't look so good anymore, don't they? Because the membranes broke. So in the ideal case, they will get to exactly the same shape, but we destroyed them, essentially. But let's see if they still taste that good. Let's see. We have a very clean desiccator, otherwise I would not eat out of it. Every now and then we put a little cyanide in there, but would you like to taste one? Okay. You too? Yeah. Okay, there you go. Anybody else? Careful. Don't sue me. All right. Good. That way I don't have to eat them all. One for the gentleman on the side there. He's so patiently waiting. It goes good with the apple and peanut butter, actually. Okay. All right. So P times V is a constant. You see it? Huh? You see it here. Now, there's another possibility, and many of you are aspiring to go to med school. When you breathe, you have a certain volume. Your lungs have a certain volume. And when you change that volume, there must be a pressure change. And so the lungs are not a muscle. But you have a muscle. What's that muscle called? The diaphragm. So when I breathe in, I get a big chest cavity, and the air actually gets right into it because I increase the volume, and the pressure has to flow in. So now if I breathe out, the chest cavity goes smaller, and the air rushes out. That's all breathing is all about. So that's when you hit somebody right here. I shouldn't be saying that. Okay? You hit them on the solar plexus. That's what happens. So that's why the boxers go for it. Okay? There's not much you can do. That's why they protect themselves. So if we could show that here and put the lights on, please, that we have a good view of that baby. The lights up there. Yeah, that's good. So this is a lung model. So these are the lung. How you call them? The two lungs, okay? No, they have a there's a German name for this actually, but also an American. So these are pretty dirty looking lungs. You must have been a smoker, okay? So I have a membrane here. I'm going to pull on here, and I'm going to increase the chest cavity. Look at those things here. And now I decrease the chest cavity. I breathe out, and it comes right out of here. And you can listen to the breathing of my guy here, okay? Look, I'm your father. Okay. This is how breathing works with our lung model. And this is Boyle's law. P times V is constant. You getting it? Good. Excellent. All right. P times V is constant. You can put the light off again. Thank you very much. Thank you in the booth. So we also can define the compressibility. That means this is the delta V over P times 1 over V minus times 1 over V. So that this value, of course, as you go up, here, for example, this is the change in V over the change in P. Okay, that's the differential of this. And so the change in V is very large, the change in P is small, so that would be a larger number. Now you can have the compressibility. We go to here, for example. Now you see the change in V is not as large, but the change in P is much larger. Okay, you need to change tremendously the P to get that volume. With this, that means this will be larger, so that number will be smaller itself. The absolute number is minus. And so just that you have seen that there's something called compressibility. And this now is, of course, you have a very small change in V and a very large change in P. And so now, diving. Who is there? Scuba divers? Any scuba divers here? Okay, good. I will talk about scuba at another time and give you some other stories, but when you scuba dive, you have we assume that at the surface where we are here at sea level, usually you dive in the sea, except in very high mountain lakes. But if you dive here at the sea or at sea level, the atmosphere is about the pressure is about 1 atmosphere. That's what we have here, okay? So every 10 meters, or 33 feet, the pressure goes up by 1 atmosphere. So if you're at 10 meters, the pressure is 1 atmosphere to begin with, plus 1 atmosphere of water pressure. That's 2 atmosphere. At 20 feet, it's 3 atmosphere. At 30 feet, it's 4 atmosphere. At 40 feet, it's 5, and at 50 feet, it's 6 atmospheres. Okay? So you go down, and the pressure increases. You have this tremendous pressure on the diver, and so the pressure is on the chest and on the lungs and everything. So if you now would ascend, go up, you have different ways of ascending. You can go, and we're going down to 50 meters, which is pretty low. You can ascend to 30 meters, or you can ascend from 20 meters to 10 meters, or from 10 meters to 0 meters. These are the 3 cases I give you. And now, let's assume that you do something which you should not be doing. When you do this ascent, you hold your breath. So that means the volume, because you're ascending, the volume of your lung increases. All right? So you have the volume down. P times V is a constant. You start out at, let's say, at 60 feet, or at 20 feet, or 50 feet. We call this pressure 1 and volume 1. Okay? And then you come up to the next level, where either 30 feet or 10 feet. You call this pressure 2 and volume 2. And this is constant, because we didn't say that the temperature changes. Okay? That's a constant. Now you have these 2 equations. Now I want to know, what is the volume when you go from situation 1 to situation 2? Okay? Why don't you think about this and give me an answer? Which one poses the gravest danger if you hold your breath, if you ascend? Is it A, from 10 to 0 meters, or from 20 to 10 meters, or from 50 to 30 meters up? Ascent means going up. Why don't you think about this? P times V is a constant. P1 V1 equals P2 V2. And I want to know what V2 is. Okay? You don't need to know actually V1. Just to get you used a little bit to this stuff. Okay. That's what you think it is, isn't it? What does the diver say? Okay. So that's why we need to know some physics, and that's what we're doing here. So I disagree with you. That would be sort of the logical thing, wouldn't it be? But you don't have to write logic, okay? You need to calculate it. So that's sort of the intuition that you let. Well, I go from 50 to, I'm very far down there, I go to 30. Oh, must be the IHA. No, it's not, okay? So P1 times V1 equals P2 times V2, and so P1 times, I don't have it here, so you can, V2 equals what then? V2 equals P1 over P2 times V1, isn't that right? Okay, why don't you put the P's in there and see what you get, okay? Discuss it with each other. Come on, wake up. Is it still raining out there? It's a dreary day, though, huh? We need the rain, though. Oh, I need to start it, too. These minor details. Okay, you have even more time to talk. So the temperature we consider constant, okay? The water doesn't cool down as much for our calculation. Exactly. So what is it? Huh? Yeah. And the other two are the same, actually. Yeah? What is it? That's correct. Yeah. 1 is 6 over 4. 1 is... Okay. How on earth did you get this? That's pretty good. So I gave you the solution and you took it. I didn't give you the solution, I gave you a way to the solution, okay? You did it yourself. Excellent. Very, very good. So we have here, this is our equation. This is a constant. P1, V1 is the one down there, okay, the lower one, and the higher one is P2, V2, and this is always a constant, okay? As you have seen, when the pressure changes, the volume changes accordingly. The pressure goes up, the volume goes down, or the volume goes up, and the pressure goes, no, the volume goes up, and if the volume goes up, then the pressure goes down, exactly. Okay, good. So now we group this is V2 is P1, V1 over P2. So this V1 is a fixed volume, and P2 and P1 is just what we are changing, is that right? So with this one, V2 is, what is this? V2 is P1 is 6 atmospheres divided by 4 atmospheres. 6 by 4 is 1.5 times the volume. So you have a 1.5 times increase of the volume when you go from 50 to 30 meters. Let's see if we go from 20 to 10 meters. So this was 3 over 2. That is 3 over 2. That's also 1.5. This is the same, actually. Okay? But when you really get in trouble when the volume doubles, okay? You also have trouble when it's 1.5. Actually, you're in trouble if you hold your breath, okay? Don't hold your breath when you go up, okay? But that's just for the experiment here. So this would be 1 atmosphere. This would be 2. 2 over 1 is 2. It's twice the volume when you go from 10 meters to 0 to the surface, okay? Did the diver say that you have to breathe a lot when you got close by the surface? Doesn't talk to me, okay? Yeah, okay, good. Thank you, I appreciate it. Okay, so A, alrighty, good. Now, we are now 100 years further, so they knew a lot about this. So there are these 2 French guys. The one is Jacques Charles, and he lived in the middle of the 18th century, 1746, that's a good 100 years later, and till 1823, even till the 19th century. And he was the first person to make a solar